Hello, this is Miss Moore, and today during chemistry we're going to discuss polarity. Today's essential question: what makes a molecule a polar molecule? All right, let's start with a quick review of bond polarity. So a polar covalent bond is a bond in which the bonded electrons are not shared equally. The electrons will be closer to the more electronegative atom. So the degree of polarity depends on the electronegativity difference between the two bonding atoms. And the greater the difference in electronegativity between the two atoms, the more polar the bond. The more electronegative atom will have the electrons closer to it, okay? And a polar bond will result in what we call a dipole moment with a partial negative charge on the more electronegative atom and a partial positive charge on the less electronegative atom. Okay, let's talk about electronegativity really quickly. As you know, I hope, that the basic trend of electronegativity going across the period is it increases going across the period and it decreases going down a group. Okay, and that pattern holds fairly well, but you also might want to be kind of aware of some of the actual electronegativity colors, or at least sort of strengths. And being that polar covalent bonds basically come from the nonmetals, we'll just talk about that area right there. All right, so starting with the purple, which is nitrogen, oxygen, and fluorine, as well as chlorine and bromine. So nitrogen, oxygen, and the first three halogens. They are, okay, let's say super strong. They are super strong, okay? And then next we have the blue guys, bluish, I guess, which includes carbon and sulfur and selenium, as well as the last two halogens. They're strong, not super strong. All right, and then the rest of the nonmetals, all these orange guys here, are kind of strong, Okay, so if two superstrongs bond together, there will be a nonpolar covalent bond. So these guys. If two strongs bond together, nonpolar covalent bond. And if two kind of strong bond together, nonpolar covalent bond. However, if a strong bonds with a superstrong, or if a strong bonds with a kind of strong, or a superstrong bonds with a kind of strong, we will end up with covalent or polar covalent bonds. Okay, so you should kind of know those, that again, the nitrogen, oxygen, and the first three halogens are super strong, that carbon, sulfur, selenium, and the last two halogens are strong, and everybody else is kind of strong. If you can kind of keep that in your head, it'll make this polarity stuff a lot easier. All right, on to the new stuff, which is molecule polarity. So we're talking now, does a whole molecule have a polar or non-polar character? So like a polar bond, a molecule can be polar with partial negative and positive charges. The polarity of a molecule, however, depends on two things. It depends on the electronegativity differences between the bonded atoms And the new thing is the arrangement of all of the atoms in the molecule. And I'll show you an example of that in a moment. So the dipole moments of polar bonds can cancel each other out, resulting in a nonpolar molecule with polar bonds. Right, so now let's try a couple examples of molecules with polar bonds and see how we do. Okay, so let's try first the molecule carbon dioxide. So carbon atoms have 4 valence electrons, and oxygen atoms have 6 valence electrons, giving us a total of 16 valence electrons. So when we draw the Lewis dot structure, we're going to end up with a carbon double bonded to 2 oxygens. And we still have 16 electrons. We should also identify the shape, and the shape is linear with 180 degrees between each of the atoms. All right, so then next we need to figure out if this bond is polar or nonpolar. So let's look at our electronegativities. We have oxygen and carbon, and remember that carbon is has a strong electronegativity, and oxygen is one of the super strong. So there is going to be, those bonds are polar with the electrons shifting towards the oxygen. So the way we draw that is an arrow showing that the electron is closer to the oxygen, and we'll make a little positive sign there showing that the carbon is partially positive. And we have to do that to the other side as well. So that is showing this yellow here is showing our dipole moments. All right, so now the big question, is this molecule polar or nonpolar? Well, just looking at the drawing, we've got this oxygen here pulling the electron this way, this oxygen here pulling an electron that way. They're pulling in equal and opposite directions, right? Which means we're going to end up with actually no polarity. It's going to equal out. They basically cancel each other out. So carbon dioxide is a non-polar molecule. All right, let's try another one. How about water? Water is always good. So hydrogen has 1 valence electron. Oxygen has 6, giving us a Lewis dot structure like this. Oops, messed up there. Try that again. There you go. Lewis dot structure like that. And the shape is going to be bent, which means it's going to look more like this. All right, so now let's look at polarity. Oxygen and hydrogen. So oxygen is again one of the super strong. Hydrogen is kind of strong, right? So I guess use pink this time. We're going to have polar bonds with the electron being closer to the oxygens. So now this time the oxygen is pulling both the electrons closer to itself, right? Making this making the oxygen partially positive, the hydrogens partially negative. So this is going to be a polar molecule. So basically what you want to do is figure out, do the polar bonds cancel each other out, add together? or somewhere in between. All right, so let's go through the rules of determining molecule polarity. So determining the polarity of a molecule. So first of all, we draw the Lewis dot structure for the molecule and determine its Vesper geometry. That's really important. You need to know the shape. So you can see the angles of the bonds, figure out if the bonds line up, the polar bonds. Okay, so next you need to identify if there are any polar covalent bonds. Sometimes there won't be. But if there is, the next thing you need to determine is if the polar bonds add together to form a net dipole moment, like water, or if the dipole moments cancel out, like carbon dioxide. And that's it. That's all we have for today. Have a good one.